Thanks for having me here today. Thanks to Maro for pointing out the opportunity and getting me the slot to talk to you all. Real pleasure to be here. Sorry if you thought this talk would be in Armenian. It's not. So I'm sure you're all very good English speakers, but I'm going to talk very slowly. That's not a choice. So I had a night out in Yerevan last night, and I discovered your brandy called Ararat, and they have lots of different flavors, and I tried to work my way through them. So I'm naturally a little bit slow today anyway, so hopefully that will work for everybody. I'm Robin Smith. I am a lecturer in nuclear physics at Sheffield Hallam University in the UK. So it's the fifth largest university in the UK in terms of student numbers. It's an ex-Polytechnic university, so a very teaching-focused institution, but in more recent years we're increasing the research that we do in the university. And my role is to increase the nuclear physics research that we are undertaking. And I want to talk to you today about a very specific small part of what I do, which is the field of nuclear data. Okay, so I recognize a few of you were in the talk upstairs a few moments ago about nuclear energy. What you can see in this picture here, although the color is a little bit off, there are 3.5 nuclear reactors here. 3.5. Okay, so this is in the UK. It's in a place called Hinkley Point. Hinkley Point is a site near the ocean where we have a series of nuclear reactors. We have Hinkley Point A and B, both very old, advanced gas reactors that have been operating for, 40 years or more, probably. You have a third reactor being built over here, Hinkley Point C, costing a lot more than it was initially forecast to cost. Okay, as all nuclear reactors tend to be, as was mentioned upstairs. So that's, hold on, so we have 1, 2, 2.5. So where is the third nuclear reactor? Yeah, exactly, right? So the sun is the extra nuclear reactor here. And although they work in different ways, I'm going to talk to you a little bit about the nuclear data needs in order to drive forward new nuclear reactors that are being built worldwide, where the gaps exist in the nuclear data, and also what nuclear data are needed in astrophysics in order to understand how stars will evolve throughout their lifetime. Okay, so I guess this is the kind of thing you were maybe expecting from this conference. The astrophysics maybe not, but this is what you have today. Okay, so what are nuclear data and why should you care about them? Okay, so why should you have any interest in what I'm saying today? It's probably a pertinent question to ask at this point. Okay, so what's a nuclear data? So I didn't know what the audience would be here. Who is a physicist here?
Basic physics.
Basic physics, you're a physicist?
Yes.
Basic or expert?
Basic.
Okay. But no, everyone else is what? Software? Lots of software people. Okay. Well, good. I started very basic for the benefit of everyone who's not a physicist. So maybe I'll start with a joke. Why can you never trust an atom?
Because it's very small.
You can trust small people. That's okay, right? Why can't you trust an atom? Because they make up everything. Okay. They do. They make up everything. So here's a classical picture of an atom. You've probably seen this. In fact, I was walking around the market in Yerevan yesterday. You get these little Soviet pin badges, right? And lots of atomic energy imagery that looks a lot like this. This is a classical picture of the atom. So in the center of the atom, you have this atomic nucleus. And around the atom, you have electrons that are orbiting. Now, in this picture, they're orbiting like planets. would orbit around a star. In reality, the dynamics of the electron's motion, that's all dictated by quantum theory. Okay, so all of these electrons are waves and they're like floating around in the atom. But we won't get into quantum mechanics too much. But this is a very simplistic picture of the atom. And an atom is 10 to the minus 10 meters in size, roughly. Okay, you know, that's one angstrom. 1 angstrom is a unit of measurement. So 10 to the minus 10 meters, so a tenth of a nanometer. And in all the pictures you'll see of atomic nuclei, the nuclei look kind of like this. So you'd be forgiven for thinking a nucleus is what, like a quarter of the size of the atom, okay? But that's not true, okay? So it's very small, yeah. So it's actually around 100,000 to 1 million times smaller than the whole atom, okay? So it's very, very tiny. Atoms themselves are pretty small, okay, as you pointed out. But the nucleus is particularly small, okay? But despite the fact that it's so small, 99.9% of all the mass of the atom is concentrated into this very tiny space that we call the nucleus. So just to give you an idea of how unimaginably dense the atom is, imagine rounding up every human being on the Earth. How many are there? 8 billion people now, something like that? How big do you think the space would have to be to compress all the people to get the density of the nucleus? Very high density object.
Horizontally, you mean?
No, just get every person and just squeeze them into a volume. How big?
I mean, size of this room?
It's a good guess. It's a very good guess.
Yeah, I think the size of this room.
Yeah? Anybody want to make a different guess?
An apple.
An apple. You're getting closer, right? So actually, to get an object that would be the density of the atomic nucleus, you'd get every person on Earth and squeeze them into a playing die. Okay? So imagine how dense that object is, okay? And everything that we have around us contains these small, tiny objects with this unimaginably high density, okay? Now, I didn't include this slide on, because I thought I had a very tight time frame. Although the atom is very, very small, the nucleus is very, very small, very, very heavy, you'll see that it's made up of these things called protons and neutrons, the nucleons that make up the nucleus. Now, typically, we associate things that are heavy with being very slow, right? If you've got a very dense object, you'd think, oh, the things that are inside that object are maybe moving very slowly. But the protons and neutrons inside the nucleus are moving around, let's say, 10% of the speed of light. Okay, so not only do we have an object that's incredibly, oh, doesn't work. Okay, yeah, of course. We have an object that's incredibly dense, incredibly small, but all of the components of that nucleus are moving around incredibly fast. Now, although many of you here aren't physicists, you all probably have heard of one physics equation. The most famous physics equation, E equals mc squared. Yeah, everyone's heard of this. So what E equals mc squared actually means is that in physics, mass and energy are interchangeable with one another, okay? Everything that has a mass has an associated energy. Because the nucleus inside the atom is so dense with mass, it means that it actually contains a lot of energy, okay? Relatively huge amount of energy, actually. So to give you an idea of this, I don't know if it was mentioned in the talk upstairs earlier, but the amount of energy that's locked up inside 1 kilogram of coal compared with 1 kilogram of uranium, it's around 1 million times higher in terms of the energy that's stored within uranium. And that's all because the energy is coming from inside the atomic nucleus, which is this very, very dense object. Okay. So that's a little introduction to the atomic nucleus. What are nuclear data? Okay, so we'll answer what are nuclear data before we talk about why you might care about them. So in a nuclear reactor, there are nuclear reactions that take place, as the name might suggest. So what happens in a nuclear reactor? You have a heavy nucleus, typically uranium-235. A neutron comes in, is absorbed by the nucleus. That nucleus splits. The fragments that it splits into have a different mass to the original nucleus, and that's what releases energy. And the energy is released in the kinetic energies, or the speeds of these two fragments, along with several neutrons that are emitted as well. Okay, so that's, yeah.
Upstairs, I also saw that the question is about neutrons.
Mm-hmm.
But what about protons? Because they have the equal number in the nucleus.
Mm-hmm.
So if you have they should have same amount, count of protons, and neutrons should be the same. So if we are bonding with neutrons, and what about protons? So they are like cracking to become the energy.
So the nucleus, what charge does the nucleus have? Is it positive? Positive charge. A proton also has positive charge.
It actually carries positive charge.
Yeah. So if you had a proton coming here, it would get repelled by the nucleus, and they would never meet.
They would never meet.
But they could meet if that proton had very, very high energy. Okay. But neutrons can have very, very low energy and still be absorbed by the nucleus and cause this reaction to happen.
But when it divides, what's happening with the proton?
So typically, the reason for this is, maybe a pen is quite a good thing to have here. So in nuclear physics, there's something called the Segre chart, and it's like the periodic table of the elements, but for nuclei. Okay, so on this axis here, we have the number of protons, the proton number, which you might know as Z from chemistry, and here you have the neutron number. Okay, so if you had nuclei that had equal numbers of protons and neutrons, they would lie along this line. Okay, but for reasons that I won't go into, when you get to much heavier nuclei, the line bends over like this. So heavy nuclei like uranium, they have a lot more neutrons than they have protons.
So amount is not equal.
It's not equal, no. So it's statistically more likely that...
Bumping new neutrons.
Yes, because there's so many more of them in... Yes, yeah. So
So it's like the amount of neutrons are going more than...
Yes, exactly.
Nucleus.
Yes, exactly.
So the reaction goes as long as there are more neutrons than protons?
No, the reason, it's just, this is the reason why after the reaction there are neutrons emitted.
Because there are more than protons.
Because there are more neutrons inside the nucleus than there are protons.
When it goes and hits another and another,
Mm-hmm.
at one point the number of protons won't be equal to
Mechanical.
Okay, well, so...
Because some neutrons are losing.
Yeah, well, exactly. So what you end up with is you start off with a very neutron-rich nucleus, like uranium. When it splits, you lose some neutrons. These become closer to this line, and so that they're more stable nuclei, and so they won't fission or release energy when they absorb a neutron or a proton. If that makes sense. So that.
It stops at some point.
Well, the fission, the splitting stops with uranium. The uranium fission happens. You split into these nuclei, which are lighter than uranium. They will maybe emit gamma rays or will alpha decay or something like this. So they're often radioactive, but they won't split and release any more energy.
So there is like a critical minimum of the split. I mean, how levels it can split, and then after it doesn't split anymore.
There's one split, but you'll see.
Okay.
You could apply more energy, I guess.
And then we have decay until it's done.
But you'll see this exact thing in a moment. Don't worry. We'll explain that. So that's what's happening inside a nuclear reactor here on Earth, or in a nuclear bomb as well, is also happening. Inside a star, it's slightly different. Okay, so this is called nuclear fission, the splitting of a big, heavy nucleus. Inside a star, we have the fusion of light nuclei to release energy. Okay, so if you look at the sun, don't do it for too long. It's not a good idea. I'm not advocating that. If you look up at the sun, the energy that's being released is due to fusion reactions. So light nuclei fusing together to make heavier nuclei. Opposite process, exactly. So something like this might happen. They come together, they fuse, and they produce some heavier nuclei, and that releases energy as well. At the moment, this is an energy source up in the cosmos, but worldwide there's a lot of research that's happening into trying to make nuclear fusion a reality as an energy source here on the Earth as well. It has many challenges. I guess we can talk about them later if we have time. But the one advantage to this would be, so uranium, we have to mine uranium, typically in like South Africa and places like this. The fuel that we would use for nuclear fusion, are isotopes of hydrogen. And hydrogen you can find in water. And we have a lot of water here. Okay?
Hydrogen becomes lithium?
The hydrogen will fuse to form helium. Yeah, in a slightly different reaction to what happens in the stars, but it's a similar process. Okay, and yeah, we have lots of hydrogen. In fact, if we could get fusion energy to work, I think we could power a village with the equivalent of one bathtub full of water, something like this. That kind of scale. Okay, so there's a lot of energy density in both of these types of processes. This has potential to be more powerful, but it's more difficult to harness that physically. The engineers worry about that sort of thing. Okay. So, nuclear data. What are nuclear data? So, every nuclear reaction that can happen, okay, you go to the Segre chart, you choose a nucleus, you choose another nucleus. When they come together, nuclear reactions can happen. Okay, so for example, for nuclear fusion, you might have tritium, which is heavy hydrogen, plus deuterium, which is another isotope of heavy hydrogen, and that will produce helium plus a neutron. Okay, so this is the kind of reaction that we want to harness in nuclear fusion power stations. Okay, but you think, okay, so hydrogen, helium are somewhere down there, but we have 3,000 or more nuclei. Okay, all of them might want to interact with each other. Okay, when they interact, different things can happen. And so we might want to know several things. Okay, so what's the probability of a nuclear reaction happening? If you force two nuclei together, what can happen? And what's the chance of that happening? Okay, sometimes nuclei can come together and they just bounce off and nothing happens. But sometimes they come together, a reaction would take place, and we want to ascertain the probability of those reactions actually happening. Okay, so that's one element of nuclear data. Another element is the reaction products. So you have two nuclei come together, a reaction happens, what nuclei get emitted after the reaction? Okay. Very important question for nuclear power. Are the reaction products radioactive? Okay, so one of the issues that the environmental activists have with nuclear energy is that the waste or the products that are produced after nuclear fission are actually radioactive and are not safe in many respects. If you dig a big hole in the ground and hide them down there, I think it's okay. But nonetheless, it pays to really understand how radioactive the products of these nuclear reactions actually are. And then finally, also very important for understanding the operation of a commercial reactor, how much energy is released in a particular reaction. Okay, so these are the four key elements of nuclear data that we as nuclear physicists really want to understand. Okay.
This is
By experiment, yeah. So on Earth, yes. So I think we can learn something about nuclear processes in stars, but typically we try to recreate the conditions on Earth and actually try and experimentally measure these reactions in a laboratory. Yeah, and that's what I do in my job generally. Why should you care? Okay, nuclear data doesn't sound particularly exciting, I don't think. Anything with the word data in is not exciting for some people. Maybe the software people like that kind of thing, okay? You're all scientifically minded, okay? But for the general population, maybe data is not an exciting word, okay? So why should you care? Okay, so, well, it turns out that really understanding nuclear reactions, understanding what happens when nuclei meet, how much energy is released, is key to safe and efficient operation of nuclear reactors. Okay? Now, I'm guessing you have a mobile telephone. Okay? You use a computer. We're looking at a projector. All of this uses electricity, and we need a reliable way of generating electricity. Okay? And there are some caveats and difficulties there. Okay, so I wrote this from the perspective of somebody from the UK, but I'm sure in lots of places in the world we have these same initiatives. In the UK, this was in 2019, so just before this horrible pandemic, and the world was a normal place, okay? In 2019, the UK passed a bill that requires us to bring all greenhouse gas emissions down to 80% of the value that it was in 1990. It's the year I was born. Okay? Now, there's already been a reduction of 40%, but we need to lower it even more. And this is law, all right? So it's the law in the UK that we have to reduce the greenhouse gas and CO2 emissions by 80% by the time we get to 2050. So it's of crucial importance, at least the government believes that it is. So we're closing all our coal power stations. We are opening up offshore wind farms. We are building new dams for hydroelectricity. But really, one thing that we need is nuclear power to bridge the gap. Okay? The advantage of nuclear power over a lot of other sources is that it just provides a steady base of electricity. You get power from wind when it's windy. You get power from solar when it's sunny. You get power from... What's that?
In England.
Oh, we don't even bother with solar panels. Yeah, just don't bother. Maybe it would work here, but wind, we have a lot of wind. But these are all electricity generation types that over the course of a day or a week, they'll go up and down. Exactly. And we need a base load electricity that we can get through, at least partly through nuclear energy. I don't want to talk about how a nuclear reactor works, the engineering side of it. I'm not an engineer, so I'd be pretending that I really understood what I was doing. There's all this interesting stuff. So the nuclear physics happens inside here, and all of the extra stuff is in order to extract that energy from the nuclear reactor and actually generate electricity. Okay, so that stuff I'm not so interested in. Okay, I'm more interested in what happens inside the reactor itself. So let's zoom into the reactor here. Okay, there we go. Look at that. I made that animation myself, you know. Could you tell? I never. You can see why my career at Pixar never really took off, can't you? I thought I had a promising career at Disney, and it never happened. Maybe in the future, I don't know. Maybe when we crack nuclear physics, I won't need a job in that anymore, and I can go into my real passion, which is animation, as you can see. So we've zoomed into the nuclear reactor, and we've zoomed into an atom or a nucleus of uranium. Okay, this big, heavy uranium nucleus. A neutron comes into that reaction. It gets absorbed by the uranium, and as I said, you get fission. It splits into two or more lighter nuclei, along with several neutrons. Okay? Now, the key thing for the operation of a nuclear reactor is that those neutrons can then go on and interact with other nuclei and release more energy, and you have something that we would refer to as a chain reaction. Okay, so this is the chain reaction. You split a nucleus, the neutrons go on and split more nuclei and more nuclei. And can you see why this would be a very effective way to build a bomb? Yeah? Because you induce one fission, you produce 3, they produce 3 more, and if you're not careful, you'll get a runaway chain reaction that is, useful in some contexts. But generally, for nuclear power, we don't want that. We want to be able to control this reaction very, very carefully. Okay? And the only way that we can control this reaction is by understanding what happens to those neutrons as they pass through the reactor. Okay? So if we want to lower the energy output of the reactor, we will want to absorb these neutrons. If we want to increase the output, we need more neutrons in order to produce more reactions. So that's the general aim of what we're doing.
So the neutrons are also getting out from reactor because of this, like a loss of.
Yeah, some of them will escape. Yeah.
Yeah. So
Yeah.
this is like a problem to control them and make them targeted.
If they're exiting the reactor, we can't do anything about that. But the ones that are inside the reactor, we can use things called control rods, and they absorb the neutrons. And so this is one way of controlling the power in the reactor is with these control rods. Okay. But the neutrons interact in various different ways in the reactor, even without control rods being involved. So I'll show you some processes, some examples of what actually neutrons do in the reactor, and these are the processes that we really need to understand. Okay, so let's talk about scattering. Okay? Now, it turns out in order for uranium to absorb a neutron, it needs to be moving very slowly. Okay? So you saw that neutron coming into the reaction was very, very slow. Okay? The neutrons that are released in fission are moving very, very fast. Okay? They have a lot of energy. We need to slow them down in order for them to be absorbed and cause another fission reaction. Okay? And the key way of doing this is through scattering. Okay? So do you remember in the talk upstairs how the neutrons lose their energy inside a nuclear reactor? By hitting water, yeah. In these pressurized or boiling water reactors, the neutrons will hit nuclei of water, the H2O, and they'll lose energy in that process. In the UK, we have these advanced gas-cooled reactors. They use carbon, so the neutrons scatter from the carbon to lose energy. But the physics principles are still the same.
But carbon is getting heating. Because of when something, neutron transfer
Yeah.
to the particle in the carbon,
Yeah.
transfer energy from
Yes.
to carbon.
Exactly. So the carbon would heat up. If you've got a reactor with water in, the water would heat up, and it's that heat that's used to drive turbines and generate the electricity.
So, but how you cool carbon?
With gas. So you put I think it's a CO2 gas circulating the CO2 gas. Yeah. Advanced gas-cooled reactor. Yes. So let's look at some more animation, because I made it, so you may as well enjoy it. So here's the neutron. It scatters. Now you see it's much lower energy, and it can cause another reaction, and more energy is released. However, okay, and this is an active research area that I'm working on at the moment, doing experiments to try to work this out. At some neutron energies, the probability of scattering is only known with around 35% accuracy. That's a huge uncertainty. How many people do we have in this room? 1, 2, 3, maybe like 20 people? That's 20 plus or minus 7 people, right? That's a huge uncertainty, okay? And at some energies, we only know the probability of a neutron scattering with that kind of accuracy, which is a real problem, okay? Maybe the software people are more interested in this, but the way that we control a reactor is heavily based on simulations. So the nuclear physics processes are simulated with a computer, and we use that to infer how we might want to control the reactor in real life. And if you want an accurate simulation, you need accurate data that you're feeding into that simulation.
More precise.
More precise, yeah. Certainly more precise than 35%. That's very bad.
And more than colder.
Yeah, exactly. Okay, so that's one process that is really important in a reactor. Absorption is another process that's very important. So on its route from the one reaction to another nucleus, that neutron may become absorbed by a different nucleus. Okay? Now, inside a reactor, you've got a lot of oxygen. Okay? Typically, the fuel is uranium oxide, so there's oxygen within the fuel. If you have a pressurized water reactor, you've got a lot of oxygen in the water. And the oxygen can absorb neutrons, and the problem is, at some neutron energies, we only know the probability of them being absorbed to around 30% accuracy again. So if we want to model how this reactor is actually working, well, we're severely limited by the nuclear data that we have for that particular reaction. Okay? So again, not very good, and this is why we're doing experimental work to try to build on that precision.
But how, I mean, from the engineering side, sorry.
Yeah.
How you are measuring it? Because when you are trying to measure, there is an inertia of reaction, and there is a latency when you're starting to measure and getting actual data. Because of the data processing systems like electronics and so on, it's also taking time. And during that time, the process still continues and then changing the situation.
Well, I can give you a brief discussion of how we might measure these reactions. So I work a lot with particle accelerators. So protons are very easy to accelerate. Okay? If we wanted to measure a reaction that involved protons have positive charge. So what you do, you have some potential where you have a positive potential and a negative potential. The proton is accelerated. Okay, very straightforward. The proton is accelerated. You could have a target of some material, like some thin foil. You fire those protons onto the target. You get some nuclear reaction. And then what we would do is we detect the products of the reaction with detectors, radiation detectors. So this is broadly how we measure a nuclear reaction in the laboratory. We have an accelerator. We produce a beam of particles of whatever energy we want. Maybe the same energy as in the nuclear reactor, for example. You fire them onto a target containing the nuclei that you're interested in, and then you measure the radiation that's emitted using these detectors. However, if you've got a neutron, which last time I checked has no charge, it's very hard to generate beams of neutrons, okay? And this is one of the reasons why these reactions are known with such low probability, is that it's very hard to generate an accurate beam of neutrons in order to induce these reactions and measure them, okay? So you can do it, it's very challenging, but this is broadly how we would measure the type of reactions. The neutron production is very tricky. If we have time, we can talk a little bit more about that. But let's keep going for the moment. So the third topic of nuclear data that's really important for nuclear reactors is radioactivity. So what can happen? The neutron interacts with a uranium. That uranium will split, and it will produce smaller nuclei, and those nuclei are often radioactive. Okay? And they will emit either gamma rays like this. Hold on. There you go. Gamma rays. Or they could alpha decay or beta decay. But there's some secondary radiation that's emitted from these. Now that's clearly very important. If you finish let's say after 6 months, you remove the spent fuel from a nuclear reactor, you want to know how radioactive that waste will be, okay? And sometimes the energy that's released by these gamma rays in the nuclear waste is known only to around 10% accuracy, okay? Which is not really good enough for what we need, moving on to future generations of nuclear reactors. Okay, so those are the 3 areas of nuclear data that have a lot of holes and a lot of gaps that need filling. And that's my job as an experimentalist, to try to perform experiments like this, recreate the conditions inside of the nuclear reactor, but in a controlled laboratory environment, and measure, well, all of these things: the probability of scattering or absorption, secondary radiation, that kind of thing. So nuclear data are really important. Reactor control, the number of neutrons that are being scattered and absorbed in a reactor defines how much energy the reactor is releasing. So if you want to increase or decrease the energy output, you really need to know this. You need to know the probability, if a neutron hits uranium, what's the probability that the uranium will split? It's also really important for nuclear waste and heat. Okay, so what radioactive nuclei get produced during the fission process, and how do they decay? Do they emit energy through alpha, gamma, or beta radiation? And then finally, this is more of an economic rather than a safety perspective, but in terms of fuel inventory, how much fuel is being used inside the reactor, and where is the fuel being used most? Okay, so fueling a reactor is a bit more in-depth than fueling your car, right? You can't just throw more uranium in. It's a bit of a difficult process.
Yeah,
you have to.
Some amount of energy going to itself. I mean, from the chain reaction.
Well, so lowering the power output of the reactor takes quite a long time, because this chain reaction will continue. There's a lot of radioactivity, so doing it in a safe way is very important. So you don't want to fuel your reactor more than is necessary, okay? And
how to define the necessary?
Exactly. Well, as little as possible, yeah. So all of these things are affected by the quality of nuclear data, and I wish that I had more time so I could teach you more about these type of experiments, but really I just wanted to give you an insight into how important nuclear data are for this in this field. So I have 15 minutes left. I want to talk to you now about nuclear data, not here on Earth, in Earth-based nuclear reactors. Let's go up into the stars, into the cosmos, and look at how nuclear data are affecting how we understand stars, how they change over their lifetime, and also how they affect our understanding of the universe as a whole. Okay, so it turns out that understanding these tiny nuclear reactions that are taking place inside stars is crucial for us to understand how our universe is expanding and how big the universe is. Okay, so these really small things are affecting the universe on the biggest scale. Okay. So, a star undergoes a life cycle, okay? We all undergo a life cycle, right? I was happy when I was young, and now I'm miserable, all right? I had lots of hair when I was young, and now I don't have so much hair. But I do have a beard, okay? Everything changes in time, and stars are no exception to that. Stars also change over time, okay? So, over a very long time. So we think of the sun as this constant thing that's in the sky, but actually in around 4 billion years, the sun will completely change, okay? So our sun is a main sequence star, okay? It is defined by the fact that it fuses hydrogen through a chain of reactions to form helium. That's how our sun is producing energy, and why we're here to even talk about it, okay? So you have hydrogen fusing to form helium. That can't go on forever, because the star will use up all of its hydrogen eventually. Okay, it has a lot of hydrogen, don't get me wrong, but over billions of years, all that hydrogen will be used up, and you will just be left with helium. Okay, and a few other things, but mainly helium. What do you think happens then? What might happen to the star?
It's going to expand and becoming giant.
Yeah, so a star has something called hydrostatic equilibrium. Okay, so you've heard about this tragedy with the submarine in the Titanic recently, right? As you go deep down underneath the body of water, the pressure gets very high, right? imagine if you have a star, you get to the very center of the star, the pressure is incredibly high there, okay? And that's because all of the material in the star wants to compress in gravity and fall down towards the center, okay? So if you're in the center of the star, you have a very high pressure, okay? Now, left to its own devices, if we were only considering the effect of gravity, that star would just collapse in on itself and become very, very small, okay? What's stopping that from happening? What do you think's stopping that star from just collapsing in on itself?
Energy that's produced in core reactions.
Yeah, so the reactions that are happening in the core, they produce a opposite kind of pressure, and you get hydrostatic equilibrium, and you have a stable shape.
Distances, the particles are, I don't know I forgot the English name. What's that?
Repel.
Repel?
Repel.
In small distances.
Yes, yeah. So you're quite right. So here we have two hydrogen fusing together. Hydrogen are both positive nuclei, right? Two protons. So they will repel each other. As I was saying to you earlier, you have a proton coming to meet another proton, and they will repel each other, okay? They have to overcome an energy barrier in order to touch, okay? That's one reason why stars are so hot. They have to be hot because the particles need enough energy to get close enough to fuse together. But even so, the nuclear fusion inside stars only happens because of something called quantum tunneling. Yeah, so quantum tunneling is a peculiar effect in quantum mechanics. So imagine, here we go. So I'll try and demonstrate with this table. All right, so there's a table. If I want to push the pen over the table, I have to give it enough energy to roll up and over the top, right? In quantum mechanics, what can happen, let's say this pen is not a pen, it's a proton. And the other side of the table, there's another proton that it wants to interact with. It turns out that the proton doesn't need enough energy to overcome the barrier. It can just tunnel directly through and meet the other proton, like a ghost.
Through the space?
Yeah, through the space. So there's a space where it's energetically not allowed, but it can quantum tunnel through and cause the fusion. It's like me running at that wall and just appearing in the corridor, okay? In the classical world, that's... It's the wrong word, but in essence, that is kind of what's happening. But yeah, you're quite right. The protons will repel. The only reason that they can meet and cause this release of energy is because of this spooky quantum tunneling in quantum mechanics. But nonetheless, okay, so let's say we have this hydrostatic equilibrium. When we've run out of the hydrogen fuel, we have no outward pressure. So what will happen? Collapses, right?
But very dense.
Yeah, so it compresses down, and if we compress a thermodynamic system, what happens to the temperature? Gets higher, right? And so what that means is then you have helium, and helium, because the temperature is now higher, they can begin to fuse. They can release energy, and that pushes the star out into a new state.
So they are forming new elements?
Yes, yeah. So what actually happens is helium and another helium, they fuse together to form carbon. Then the helium can meet with carbon to form oxygen, and then you produce heavier and heavier elements this way. And so this is called the red giant phase of a star, and you produce elements all the way up to iron inside the core. Okay. For reasons I won't go into right now, iron won't fuse together to form heavier elements. It doesn't release energy in that way. So again, a similar thing will happen. There's no more fusion in the star, and so the whole star will collapse yet again. Okay. What can happen then? for a star like the Sun is that the outside parts of the star are shedded away into something called a planetary nebula, leaving a white dwarf star, which is just a collection of matter that is hot, and so it's glowing, and over time it just gets dimmer and dimmer, and will just dim into the cosmos, and you won't see it anymore. Okay, so that's one thing, that's one way a star can end its life. Not a very exciting end to a star's life, okay? But I like to think at my funeral, they'll play some fun music, right? You want to go out in a bang, right? So turns out that if you have a star that is heavier than our Sun, giant stars, that's around 1.5 to 5 times the mass of the Sun, when the star has used up all of its hydrogen, it starts to burn helium. Now, instead of a red giant, you have a super red giant. Very exciting name. Very, very creative name that the scientists came up with. They have a super red giant. Again, that burns elements all the way up to iron. When you reach iron, the star basically explodes into something called a supernova explosion. So these are the brightest, brightest, most energetic events in the cosmos. And if we were to see a supernova at some point in the galaxy, it would be, in the sky, it would appear as bright as the moon. Okay? There's that much energy that's released in one of these. The brightness would appear, and you would be able to see it with the naked eye. After that supernova, you can have a neutron star left over or a black hole. Both very...
Oh, it's not a hole, actually. It's like a very high-density matter. It's not a hole.
We don't know what's inside.
It's like a plane.
So,
is it hole or not?
Well, so if I throw this pen up into the air, it falls back towards the Earth, right? If the Earth was heavier, it would fall back more quickly, and I'd have to throw it even harder to get it up into the air, right? Black holes are so heavy that if you shine light upwards, the light is drawn back down into the black hole. That's why they're black.
It attracts light also.
Everything attracts light, but all gravitational bodies attract light, including the Earth, including our Sun. But this is so heavy that not even light can escape. Okay.
But it's not the hole exactly. It's like matter.
I think we should watch what Interstellar. Interstellar to learn what happens inside a black hole. Nobody knows really. It's certainly not my field of expertise. But one thing I wanted to draw attention to is this supernova explosion and why they're so useful for understanding the universe. Okay, they're very, very useful. So here's a picture of a long dead supernova where you can see all of the matter, propagating out into space. I think it's called the Crab Nebula, I think. But I'm not an astronomer, so I don't really know. Okay. So, the reason that these supernova explosions are so useful is because they give us an insight into how fast the universe is expanding. Okay? So, it turns out if we look out into the cosmos, we look at our neighboring galaxy or another galaxy, on average, everything is moving away from each other. Okay? Think about blowing up a balloon, and you have little dots on the balloon that represent the galaxies. Everything is expanding away from each other. Okay? And that's because, as far as we know, we started life 13.7 billion years ago in this Big Bang, and typically explosions throw everything outwards, and so the universe is expanding outwards from this one point.
And the expansion is accelerated?
Well, that's still to be determined. But so there are different models for how the universe will die, and ultimately over time, we want to know, will that universe keep expanding? Will it get faster and faster? Thank you. Or will it collapse in on itself? Okay, will it just, imagine like a piece of elastic. It gets bigger, and then gravity might bring it all back together. We want to find out if that's going to happen, and the only way that we can find that out is by measuring how fast everything is expanding and how far away different galaxies are from the Earth. Okay, it's really important that we know how far different bodies are from our place in the universe. The way that we do that is using these really useful supernova explosions. Okay? So I'll give you a little experiment. So here is my torch on my phone. Pretty bright. Okay, there you go. Now if I had that torch really close to your face, it's very bright, right?
Right, yes.
If I went all the way over here, it's very dim. Okay? So if you know how bright something is, and then you measure its apparent brightness, you can measure how far away that object is. You can infer how far away it is. So if we know the brightness of a supernova, if we measure it through a telescope, we look at how much brightness we actually observe, and we can calculate how far away that supernova is from the Earth. It's basically a way of measuring distances in the universe, these unimaginably large distances. That's why supernova explosions are really useful. The problem is this method relies on us knowing how bright a supernova explosion actually is. Okay? And remember, the supernova explosions, they happen at the end of this life cycle of the star, and actually the brightness of these explosions depends on the nuclear reactions that have been taking place. Okay? How much, at this stage, how much iron is produced, how much neon, how much every element is produced in this stage dictates how bright that supernova explosion will be when it finally explodes. And so understanding the underlying nuclear physics of stars dictates our measurement of distances across the whole universe, which I think is pretty amazing. And yeah, the nuclear data are the limiting factor in really understanding how bright these explosions are. And I just think that it's quite cool, quite neat, that physics on the smallest scale, on the nuclear scale, is affecting our understanding of the universe on the biggest scale. Yes, exactly. So I want to summarize because I only have a minute or two left. So we talked about nuclear data here on the Earth. Nuclear data are really important for the safe and efficient operation of nuclear reactors on Earth, understanding the radioactivity of nuclear waste. Up in the cosmos, I gave you one example. Okay? We need to understand the life cycle of stars. That's all underpinned by the nuclear reactions that are taking place. That helps us to understand the brightness of these supernova explosions and helps us to calculate the expansion and the age of the universe. Okay, so that's it. Thank you for your attention. I hope you could understand my slow Ararat-induced speaking today. Thanks. I think we have a couple of minutes, don't we?
Can we exchange contacts?
Yes, of course. Yeah, absolutely. Well, nuclear physics and Ararat go together very well, I think. So.
We have a country built around them.
Women's Ararat branding.
That's what I meant, yeah. Any questions? Or you just, yeah.
Are you doing any research in Armenia or you're just guest speaker?
I came for vacation and then Mauro invited me to. But it's good leverage. I can go back to the university and say, I wasn't on vacation, I was working, so you can give me an extra day of holiday. But I'm meeting the director of the institute on Tuesday, so hopefully we can maybe talk about possible collaboration in some research. So. And have more branding. Yes, exactly. Paid for by the university, I hope. Yes, hello.
Yeah, hello. And what about the redshift? It's another way to measure
Yes.
the way how galaxies move.
So the redshift measures how fast something is moving.
But not distance.
Not distance, no. So what you would do is you have one of these supernova explosions. The brightness tells you how far away it is, and then the wavelengths shifted will tell you how fast it's moving. Yeah.
Mm-hmm. Okay, thank you. But another one question.
Yeah. Okay.
I heard a theory that alternative theory that the universe not expanding. So either it's slower down or it even stops. So did you hear something about it? Because there are different different opinions on that.
Yeah, so cosmology isn't really my field, so I understand the nuclear physics and broadly how it affects our understanding of the universe. What I would say, I think that it's still an open question, so we can look at how fast objects are moving in the universe and how far away from us they are, and that will eventually tell us, is the expansion of the universe increasing, so accelerating, or is it slowing down? And if it's slowing down, that means that gravity is slowing the universe down, and eventually it will compress back down to a point again. You'll get a second Big Bang, and something like this.
Yeah, or it might be different dimensions. So for us, it's expanding, but in reality, in other dimension, it's just.
Who knows? This is why physics is so strange. Yeah, you're talking about different dimensions, and how can we as humans interpret that? Mathematically, there are interpretations. You can mathematically construct four-dimensional shapes and see how they have projections in 3 dimensions, but I'm not clever enough to understand that sort of thing. So, yeah.
Do you have any other means to measure the distance?
So you not on these large scales. So in our own galaxy, we can measure how far away a star is using parallax.
Yeah,
so if you look in the night sky, and then you look 6 months later, the Earth has moved to a different point, and so the star appears to move. So you can calculate how far a star is using this method. There are also stars that oscillate in brightness. They're called Cepheid variable stars, and you can use them somehow, but I'm not really sure about the technicalities. But that's all within our own galaxy. If we want to look at different galaxies on these large scales, we have to resort to this process, I think. Yeah. You had a question, I think.
Yeah, is there other fuels than uranium that can be used and it will be safer?
I mean, there are other fuels, so...
No, the other radioactive which can be used in the
yeah, so instead of uranium, so it was mentioned upstairs, there are these fast reactors. So fast neutron reactors, I mentioned that the neutrons that are produced are very fast, and we have to slow them down so that uranium will absorb them. Fast reactors that use plutonium, for example, and I think thorium as well, they will split when they absorb a fast neutron. So there are alternative fuels available. Whether one is safer than the other, I don't know exactly. Certainly, there are more efficient fuels. So the next generation of nuclear reactors, there's some discussion, instead of using uranium oxide fuels, we could use uranium nitride, because the fuel has better sort of thermal and structural properties that would make, the operation of the reactor more efficient, or refueling the reactor safer. If that answers your question a little bit. All right. Time's over. Done.
Thank you very much.
Thank you.